Hello and welcome to our presentation on investigating multimodal measures for cognitive load detection in e-learning. In traditional learning, human teachers usually try to estimate their students' cognitive load and react to it, so add further explanations when they feel like their students were overloaded and did not properly understand everything, or move on to more complex topics. While the e-learning industry is now growing rapidly, especially due to the corona crisis, e-learning platforms still usually rely on some static linear order of content, so you just go through one by one. There's not much adaptation to your current cognitive state, only a little bit of customization to what you did in the past or how well you performed in the quizzes. So the literature proposed the concept of cognition-aware e-learning, where the goal is that students stay in the optimal range of cognitive load to facilitate learning. And they propose plenty of approaches to estimate cognitive load, for example, based on consumer devices or on EEG sensors. Apart from these works that, just propose different sensors and correlate them to some measure of difficulty, like facial expressions or eye tracking features, other papers have focused on good use cases. How can you adapt it to the measured cognitive load? For example, you could recommend learning contents that are most appropriate for your current situation, or you could adapt the whole interface. On the other hand, there are some papers that go a step beyond and try to really train predictive models. For example, a rich regression model to estimate the task complexity, or SVMs for binary classification if the student will succeed or fail. However, these models usually focus on some few sensors, for example, EEG or eye tracking features. And on the other hand, they often, don't really have a learning task, but more a mental arithmetic task. So you need to add up some numbers, and depending on the difficulty of that task, you can expect the cognitive load to be high or low. So what we propose instead is to have a more diverse set of cognitive load measures, but also a more realistic study where people really learn with videos and quizzes, as is common in the e-learning setting. And then we want to try to also investigate which modalities, so heart features or skin features or eye features, tend to work better than others. For our study, we first handed out a pre-questionnaire to capture demographics, but also the exhaustion, tiredness and stress, and the background in the topics that we then chose for the later parts of the experiment. Then we attached all the different sensors, which we'll see in a bit, to the participants and showed them the Moodle environment, in which we displayed the videos, where we chose 3 different topics, namely integration, vectors and eigenvectors, each with the easy and a hard video, where the easy video captured content that was part of the high school certificate, and the hard content is part of the curriculum of the university. And to ensure a very similar presentation style, we used the Mathe by Daniel Jung channel, where we have the same speaker presenting in the same way, so to limit, effects based on a different teaching style. And after each video, we asked them to assess cognitive load and difficulty. Following the videos, there always came a quiz with multiple questions, and again, they had to assess the cognitive load and difficulty of solving the quizzes. Then there was a small break task to limit the interference between the content items, and we did so for all 6 contents, so we counterbalanced across the 3 topics. And in the end, we had a small post-questionnaire to again capture exhaustion, tiredness and stress. This image shows the sensor setup that we used, so let's go through that one by one. First, we have some rating scales, so subjective measures. One for cognitive load, which is in solving or studying the preceding problem I invested very, very low mental effort to very, very high mental effort. And the difficulty scale, namely the preceding content was extremely easy to extremely difficult. And both these questions appeared within the Moodle environment after each video and after each quiz. For the quizzes, we also captured how long it takes the students to solve them and how well they perform, so how many questions they get right and wrong. As a behavioral feature, we use the Microsoft Kinect V2 to capture the skeleton, and with it we calculate the distance between the head and the screen, hypothesizing that you come closer to the screen when you are cognitively loaded. For eye tracking, we integrate the Tobii 4C eye tracker and a webcam. With the webcam, we just calculate the openness of the lids which you see on the right. So that's the eye aspect ratio, and with the eye tracker we capture blinks, fixations, saccades, of course the durations. We re-implemented a paper to capture if the user is searching for something, and we integrate pupil diameter measures such as the index of cognitive activity. As cardiovascular measures, we integrate the Empatica E4, the Polar H7, and the Garmin Forerunner 935, and with them we capture the heart rate, but also the RR interval, from which we calculate the heart rate variability measures, RMSSD, SDNN, PNN50, and also blood volume pulse measures. As skin measures, we again use the Empatica E4, the Garmin Forerunner, but also the Microsoft Band V2, and with them we capture the galvanic skin response, which we use then also in the LeaderLab software to calculate some high-level features on them, and we use the skin temperature as a measure. Here you can again see an overview of all the measures. So we have 2 subjective scales, 2 performance measures, 1 behavioral measure, and lots of physiological measures for eyes, heart, and skin, and of course these can be combined in several ways. We can distinguish these features into 2 categories. On one hand, single features, so for example the subjective ratings, where we just have one value across some time interval. And on the other hand, we have continuous streams of data, for example for the heart rate, which we then first normalize by the participant's mean, and then we compute 5 simple features, so the average, the standard deviation, the min, max, and the range, which is just the max minus the min. And this is what we do for all the remaining features that, where we have a continuous stream. So overall, this gives us 202 features, which we of course filtered a bit according to the literature, but also according to visual inspection. As participants, we had 21 students, 17 of them male. They were studying computer science, so we ensured that they had already passed the relevant math lectures so that they have a comparable background in the topics that we chose for our experiment. They are of course rather young. Half of them had good or very good e-learning experience on different platforms. They found that the topic vectors is significantly easier than the other 2 topics. In terms of tiredness, exhaustion, and stress, we could not find a significant difference between before and after the experiment, which is good, so there are no strong tiredness effects that might have biased our data. And they had a high motivation to follow the videos and a very high motivation to perform well on the quizzes. When we look at the ratings that the participants assign to the contents, we see that for vectors, eigenvectors, as well as across the 3 topics, the differences between the easy and the hard videos or quizzes were there and were significant. However, for the integration case, that was not the case, so we also need to consider the topics individually. When we look at the correlations between the cognitive load ratings and the difficulty ratings, we see that they are highly correlating. So for participants, the 2 things were apparently very strongly related and almost the same. And if we look at the results in the quizzes, we see that participants were indeed much faster for the easy than for the hard quizzes. But in terms of how well they answered the questions, there was only a marginal difference between the easy and the hard topics. One very simple thing to investigate is how strong is the link between all of these features and our 3 target variables, so the difficulty of the content, so easy or hard, as well as the subjective ratings, subjective cognitive load, and subjective difficulty. However, we have very many features and 3 targets, so we cannot really look at all correlations. So what we did as a start was just to look at the highest correlations of some feature towards these 3 targets within our cases across videos, within the integration topic, within the vector topic, and within the eigenvector topic. And what we see here is that the correlations are overall quite good, right? We have values up to 0.53 actually, and many around 0.4. But for the across video cases, even the highest correlations are still pretty bad, 0.14 to 0.18. So this suggests that it will be much harder to predict this case. So let's try to predict. First, the intrinsic difficulty. So this is a binary classification task, whether it's a high school certificate content or a university degree content. And what is interesting here, that if we use a very simple logistic regression model, we achieve some 80 to 90% accuracy for the quizzes, but only some 70 to 75% accuracy for for the videos, except for one outlier, for which we unfortunately don't really have an explanation. We think it's some artifact in the data. So might it be that the degree of activity really impacts how well you can predict it? So is it much easier to predict within quizzes where people are actively engaged? If we look at the regression results, so trying to predict the subjective difficulty or subjective cognitive load, we see that within topics we get very low mean square errors, especially compared to the simple baseline that always predicts the medium rating. So it seems to work very well here, whereas across topics it also works okay for the quizzes, not as good as within a topic, but still quite good, but not at all basically for the video case. There's only marginal gains to the baseline. And again, this might be due to the active versus passive consumption of videos and solving quizzes, or maybe also because, you know, when you only passively watch a video and the hard video of one content might not be much harder than the easy video of another content, it's of course hard to distinguish that later on. So those were the results when predicting using all features, but we also are interested in which modality is better and worse, and for this we look at the intra-class correlation coefficient, which is an indication of the extent to which different participants produce the same values of a given measure when they are exposed to the same condition. So it tells us which features generalize well from a small number of participants. And what is quite interesting is that even though all the measures are proposed in the literature, we see that only 2.5% of our features can be considered excellent in terms of ICC, 3.5% as good, 27% as moderate, and the majority of 67% as poor. However, one should note that this can also be the case because, you know, we calculate these 5 simple features on top of the raw signals. But still, it's interesting because most works don't report the ICC, and we see that many sensor features here are actually pretty bad. Well, of course, a few are pretty good as well. And if we look at the modalities that the good ones belong to, we see that almost all belong to the hard category, so all excellent ones and the majority of the good ones, plus some moderate ones. So this is clearly the best in terms of ICC. Closely followed then by heart and skin, which are both, you know, constitute some of the good and moderate features, whereas the body posture features can all be considered rather poor, so that's also quite interesting. So let's look how well we can predict based on some modalities. In this chart we have the prediction of subjective cognitive load on the left, subjective difficulty in the middle, and intrinsic difficulty on the right. So on the right we have a binary classification task, so that's the accuracy, and the two things on the left are the mean square error. We see in the blue charts what we saw already before, namely what happens when you use all features from all modalities simultaneously. The green ones are what happens when you use only features from one modality, and here we see that eye and heart apparently work a bit better than the skin features. But we also see that if you use more than one modality, so if you combine all or use pairs of two, which would be the yellow case, you get better results than single modalities. And combining the two things, namely eye and skin, is almost as good as the multi-modal case, which has all three. So, to conclude, we explored a very wide range of cognitive load measures in a rather realistic e-learning setting with videos and quizzes and 21 participants, where we tried to predict subjective cognitive load as well as subjectively assessed difficulty and the intrinsic content difficulty, so whether it's a high school or a university content, where we were able to achieve a high accuracy and a low mean square error, so many adaptations from the literature might be possible in practice. We also saw that, you know, findings achieved in some more artificial arithmetic calculation tasks could be replicated in this more realistic setting here. And we saw that it's easier to predict during quizzes than during videos, where people actively engage with the content and not just passively consume it. In terms of modality analysis, we see that from our considered features, the eye features perform best, followed by heart and last skin. But of course, when you combine several modalities, you get better results. And this extends the findings by Naismith and Cavalcanti, who didn't have the skin in their study. In the future, we want to try to get a more real-time analysis to predict the cognitive load based on shorter windows of time. and to look at the individual features and not just at the individual modalities as we did in this work. Furthermore, you should consider the limitations of the study. Of course, we only had 21 participants and 6 contents, so further studies are required in the future. Thank you, and bye-bye.